All right, so let us talk about these redox ones here. So earlier we talked about balancing sort of simple redox reactions, which you may come across some here in this study assignment as well. And a reminder, if we had something like calcium plus some chlorine, making a little calcium chloride here and do a little balancing. I think we're balanced actually in this case. We can look at this, and a reminder that this 0 and 0 in terms of its oxidation state, that is a +2 and a -1. So once again here, as we talked about earlier, we could see that the calcium is going from 0 to +2 in this direction, which means it is becoming more positive and it is going through oxidation. By default, that obviously means that our chlorine here would be going through reduction, and we could also do the same thing for the chlorine, starting at 0 and ending at -1, going that way, and becoming more negative. That also means, just for a reference point here, this would be our reducing agent, right? Which is the thing that's getting oxidized. This would be our oxidizing agent here, which is obviously the thing that is getting reduced. We could split this up into its half reactions, and we would have really our calcium here going to our calcium with a +2 charge. Once again, this is our oxidation, so we would be giving off 2 electrons. In this case here, we would then have our Cl2 going to our Cl minus. And in this case, we will, I'm just gonna, for our purposes, we'll put a 2 here, and we'll have 2 electrons here. And in this case, that would be our reduction half reaction, right? And this is obviously our oxidation half reaction. Once again, the oxidation half reaction will always have the electrons on the product side, and the reduction half reaction will always have our electrons on the reactant side. In this case, when we go to add these together, we're actually okay because our electrons are the same in each half reaction. So they will cancel here. And in this case, that will leave us our overall reaction of our calcium plus our chlorine. And again, these 2 ions would come together and make our calcium chloride. Now, if we swapped out and we did, say, silver, with, say, oxygen, here, 4 electrons. And let's say we wanted to put these 2 half reactions together. Once again, we couldn't add them together at this point because we only have 1 electron here and we have 4 electrons here. And as I mentioned, this sometimes does happen, but you always want to make sure you have the same number of electrons in each. In this case, we would need to multiply the top one there by 4, I guess, in this case. So we'll go with 4 and multiply that by 4 and multiply that by 4. At this point, we then could add them together. This will get us 4 silvers plus oxygen, giving us our Ag2O here. And in this case, if we take the 4, we'd actually end up with 2 here in this case. So in this particular case, we would have to multiply our half reactions by a common number. That's a really bad example there, but it worked out, I guess, in the end as I fix it. All right, so and simple half reactions, if you need to add them together, you just need to make sure that you do get the electrons to be the same and multiply them across. So let's talk about a little bit more complicated ones here. Now, sometimes you balance these guys in either acidic or basic conditions. And there's several steps that you want to follow when you have an equation like this. So what you would have is an equation like this. It will say balance it in either acidic or basic conditions. And we're going to talk about how to do both of those together. So the first thing that you would want to do in this particular case is you would want to break this reaction off into its half reactions. So one should be an oxidation half reaction. One should be a reduction half reaction. It may be helpful for you to sort of figure that out at the beginning. So if we did that, the iron here is +2. We did this guy, I believe, in lecture, and our chromium ends up at +6 in this case. That's -14 and -2 left over gives you a +12 that you need there for our chromium, and since we have 2 of them. The oxidation state for the iron over here is +3, and the chromium is +3. In this particular case, the thing that is being oxidized is which one? It is the iron, right? It is going from +2 to +3, becoming more positive. The chromium is going from +6 to +3, so it's becoming more negative, right? It's kind of moving to the left there on our number line. So again, here, the iron is being oxidized. That is our reducing agent. The chromium here with the +6 oxidation state is being reduced, and that is our oxidizing agent. So it's good to kind of keep those in mind as you go through this process to make sure that you sort of do everything correctly along the way. So once again here, oxidized and reduced. So the first thing that you want to do when you want to go balance these guys is just simply split off the two half reactions. How you do that is pretty much you take the two things that have the same element on opposite sides. So these two things, and the other guy has some chromium in it. Yeah. So these two things here. So this would be our two half reactions. And as we just determined, this is obviously going to end up being our oxidation half reaction. This will be our reduction half reaction in this case. So the first thing you want to do is split the half reactions. One again would be oxidation and one would be reduction. The next thing that you want to do is you then want to balance the equations. All elements except hydrogen and oxygen. So you want to balance all the elements except for hydrogen and oxygen. And the way we do that is just like we would do in the normal balancing of equation. We're just going to use a coefficient to do so. When we look at the iron, we have basically one iron on the left and one on the right, so we don't have to do anything with that. When we look at the chromium, there are 2 on the left and 1 on the right. So again, just like a normal balancing equation of a 2 in front of it, because when we are all said and done, this equation needs to basically be balanced in 2 ways. It needs to be balanced like a normal equation that you have the same number of elements on each side of the arrow. And it also needs to be balanced in terms of overall charge on the left-hand side and right-hand side of the arrow needs to be balanced as well. So regular equation, same elements, and overall charge when it's all said and done. Now that we have balanced everything other than hydrogen and oxygen, the next thing that we're going to do is actually balance the oxygen. And the way that we balance oxygen in this type of situation is that we add water to the side that needs the oxygen. So whatever side needs the oxygen, we basically add water to it. Now, when we do add water, we're not just adding oxygen, but we're also adding hydrogens. So that's going to throw off our hydrogen count. So because of that, what we do is for every water we add to one side, we add 2 H pluses to the other. And that will take care of the hydrogen balancing. So you need to add water to the side that needs the oxygen. To the opposite side, for every water that you add, you need to add 2 H pluses to maintain the balancing of the hydrogen. By the way, if you are starting out, like at this point right here, with an extra hydrogen, for example, on one side or the other, you would then just add an H plus to the opposite side. So that you could also use H plus independently of this process. If you see in one of these half reactions, there's like a HNO3 on one side and like an NO3 on the other side, or NO2 on the other side, you could just add an H plus to the other side right off the bat. Somewhere along the way, you need to add the H plus, so it's easier sometimes just to do at the beginning if you're unbalanced with hydrogens. So in this particular case, if we were to do that in terms of the iron, we do not need to do anything to the iron because there's no oxygen. But for the second half reaction, on the left-hand side, there are 7 oxygens. On the right-hand side, there are none. So for the second half reaction, we need to add 7 waters to the right-hand side. So I'm just going to write it underneath. So Cr2O7 2 minus. We're going to take 2 chromiums here and 7 waters to the right-hand side. The purpose of the 7 waters was to add 7 oxygens to the right to balance it. Because I added 7 waters to the right-hand side, how many hydrogens should I add to the other side? I need to actually add 14, which is 7 times 2 here. So to the other side, we're going to add 14 H pluses. So once again, water to the side that needs the oxygen. And then for every water, 2 H pluses to the other side. That again keeps hydrogen and oxygen balanced. Any questions up to there? All right, so now that we split it off, we balance all the elements other than oxygen. We balance oxygen with the water. We're now at the point where we're going to balance out the overall charge on each side by adding electrons. So we're going to add electrons to balance out the charge on each side. So it's a very simple idea here. Electrons are what type of charge? Negative. So you need to add the electrons to whichever side needs the negative charge to balance it. It does not need to be 0 on both sides. It just needs to be the same number on both sides. Either positive something, negative something on both sides, but it does not need to equal 0 on both sides. So for example, if we look at the iron up here, the best way to do it is just the overall charge on each side. Overall charge on the left-hand side is +2. Overall charge on the right-hand side is +3. Which one needs the negative electron? The right-hand side, right? The right-hand side needs a total of 1 electron. 1 electron gives me a -1, which gives me a +2 on the right and a +2 on the left. Any questions on that? That is also pretty good because this is which half reaction? It is the oxidation half reaction, which means electrons should end up over here on the product side. So that's why it's good to know which ones are oxidation and reduction. You can kind of check yourself. All right, so we're going to come down to our chromium one here that we obviously did a little work with. Overall charge on the left-hand side. Again, this is 14 positives. And I am not going to worry about each individual element here. This is what I was talking about before. All of those elements add up to a -2 charge. So why do it individually when it does it for you? That gives me a grand total of a lot on that side. That is a +12 happening, bless you, on the left-hand side. On the right-hand side, that is 2 times 3, which is +6. And this is 0, which means on the right-hand side, we have a total of +6. And on the left-hand side, we have a total charge of +12. The side that needs the negative is the left-hand side. And to get our +12 to +6, I need 6 electrons to do so. 6 electrons gives me a -6, and a +12 is a +6 on both sides at this point. Any questions on that there? Okay, so just to rewrite the two equations where we're at, top equation there, we basically just added some electron or an electron here. Bottom equation, we added our waters and some electrons here and our H pluses. All right, at this point, we are ready to add these two half reactions together. But again, we run into a situation like we talked about before. We could add these together. The electrons need to be the same in each one, and they're not. In the top one, there's only 1 electron. In the bottom one, there are 6 electrons. So we need to add the half reactions together, but we need the same number of electrons, right? Which is right there on the bottom where all this stuff is. So let me rewrite it here on the next page up high. So we'll go with our Fe2 plus, Fe3 plus an electron. On the other side there, 614, 6 electrons plus 14 H pluses, plus there, the dichromate, right? Goes to our other side there, which was chromium 3, and we had a 2. Did I get it all there? Maybe. How did I do that? They have an H2O. Thank you. Plus 7 H2Os. That's everything. Yeah. Okay. So we're ready to add these together. So we're going to multiply the top equation by 6. And it's not just the electrons. We're going to multiply the entire top equation by 6. And I'll write it right underneath. That will give me 6 of the iron 2. Gives me 6 of the iron 3. And now gives me 6 electrons. Now that I have the electrons the same, and by the way, the electrons are on the same side of the arrow or opposite sides? Opposite sides, which they always should be. For the chromium one, that was our reduction, and we have our electrons on the left-hand side, which makes sense. This was our oxidation, which we have our electrons on the right-hand side, so that makes sense. So I'm going to cancel out the electrons, and if you get to this point and the electrons do not completely cancel out, you screwed up. Yeah, so they need to completely cancel out. At this point, if there's anything else that's there that's on opposite sides of the arrow, you can either cancel them out completely or reduce them down. In this case, it doesn't look like there's anything else that's going to cancel out. So at this point, everybody on the left-hand side of the arrow in both equations stay on the left-hand side. Everybody on the right-hand side stays on the right-hand side. So if we do that, we got a little of 14 H pluses plus Cr2O7 minus plus 6 of the iron 2. That is everybody on the left-hand side of the arrow. On the right-hand side of the arrow, we got 2 of the Cr3 plus 7 waters and 6 of the iron 3. If I did not screw anything up, it's a 50-50 shot here. This would be the balanced equation in acidic conditions. So the process we just went through would be how you would balance it in acidic conditions. So let's see if I screwed up here. We have 14 H's. That is 14 H's, so that's good. We have 2 CRs. We have 2 CRs, so that is good. We have 7 oxygens. We have 7 oxygens there, so that's good. We have 6 irons and 6 irons, so it is balanced like a normal equation, same number of elements on each side. It also should be balanced based on overall charge on the left-hand side and right-hand side. This guy here is contributing a plus 14. This guy is contributing a minus 2. and this guy is contributing a plus 12. I'm getting that by taking the coefficient times the charge. Yeah, so 6 times 2. That gives me a grand total charge on this side of a lot, but that does equal plus 26 less 2 is a plus 24 charge on the left-hand side. Right-hand side, this guy is contributing as 2 times 3, which would be plus 6. Water is neutral, which means it's contributing nothing. And our iron here is 6 times 3, which would be plus 18. Plus 18 and plus 6, I hope, is plus 24 at this point. Yeah. So this is how these equations should end up. They should be balanced like a normal equation, same elements. And once again, the charge on the left and right doesn't have to equal 0, but it does need to equal the exact same number on both sides. You're positive on both sides, negative on both sides, or maybe even 0 on both sides, but it does need to add up to the same number. Any questions on how to balance this in acidic conditions? Now, if you need to balance this in basic conditions, there's a couple ways you can do it. I think the easiest way to do it is what we just did. You just balance it like it was in acidic conditions. At the end of the road here, when you get to this equation, you then can turn it into basic conditions relatively easy. So that would be my recommendation. You could actually add everything in earlier, but it gets a little complicated to keep track of things. So if you need to balance this in basic conditions, what we're going to do is basically just do acidic and then turn it to basic at the end. And I'm going to maybe recopy this a little bit higher. So we got 14H pluses. Plus, somebody want to read it to me real quick? Say it again. Dichromate. Okay. And Fe2 plus, other side. Okay. 7 waters. Thank you. All right. So what we're going to do here, if we need to turn this into basic, is just follow all the stuff we just did for acidic. But for basic, what we're going to do is we add OH minus to both sides. So we're going to add OH minus, which is like base, to both sides. And it's going to be equal to the number of H pluses there are. So in this case, we have 14 H pluses in your acidic equation. The way you know it's acidic is it says H plus. That's how you know it's acidic. There will be a certain number of H pluses. You're going to add OH minus to both sides. So let us do that. So to the left-hand side here, we're going to add 14 OH minuses, and that's because there are 14 H pluses, plus 14 H plus Cr2O72 minus, plus 6 of these guys gives me 2, 7, 6, and I'll go underneath here, not 6, but 14 would be good. Clear that out a little bit. Plus 14 OH minuses. Okay, now when you do this, there's definitely going to be a side where there's H plus and OH minus together. When you have H plus and OH minus, what do they make? That's 2 hydrogens and an oxygen. That's water. Yeah, that sounds good. So it makes actually 14 waters in this case. And what will typically happen at this point is, if you look on the other side, there are 7 waters. So that can be reduced down. So basically, like subtracting 7 to the other side will leave me 7 waters left over, plus my Cr2O72 minus, plus my 6 of the iron 2, my 2 of these guys, my 6 of those guys, and my 14 of these guys here. And at this point, this would be the balanced equation in basic conditions. Once again, I know this guy is basic because there's OH minus. I know that this guy is acidic because there is H plus in it. Once again, it should still be balanced. So that is 14 H's, 14 H's here. That is 7 oxygens there, plus 7 more is 14, which is right there. That is 2 chromiums, 2 chromiums, 6 irons, 6 irons. Overall, left and right, same number of elements. This water is going to contribute 0. This guy is going to contribute -2. This guy is going to contribute 6 times 2, which is plus 12, which means overall charge on the left-hand side is plus 10. Right-hand side, this guy is going to contribute 2 times 3, which is plus 6. 6 times 3, which is plus 18. And 14 times -1 is -14. That is plus 18 and -14 is plus 4, and plus 6 is plus 10. Yeah. So once again, it is balanced both in terms of charge on both sides and elements on both sides. That is probably the easiest way to do basic. It's just to do acidic, add the OH minus to both sides, combine the water, and in most cases, you'll have some water to reduce down, and then you would have your basic reaction. Any questions on any of those steps there? All right, well, I did one. You do one. All right. Take like 30 seconds and do it. I'm going to take a nap. All right, so follow those steps. Split it off into the half reactions. Balance all elements other than hydrogen and oxygen. Balance oxygen with the waters, and then the H pluses. Add the electrons, add it back together. Okay, so let's take a look. Hopefully you should be making some progress. I hope some more progress than what's up on the board. Hopefully we got a little bit past that. All right, so we're going to balance this guy in basic conditions because frankly it says basic, so why not? That's what that scribble means. We're going to first maybe take a look and see what is happening, what's being oxidized, what's being reduced. So our I minus obviously has an oxidation state equal to the charge, which is -1. For our oxygen here, that would be -2, and there's 4 of them, which makes it -8. There's a -1 overall, so that is a +7 happening there for our Mn. Once again, that's -8 equals -1 plus 7 is what you need there. Our I2 is in a standard state, which means it has an oxidation state of 0. The Mn over here, the oxygen is -2. That is -2 and -2 and plus -2 and multiplying 2. -2 and times 2. That's what I'm trying to say. That is -4. That's a +4. I need a nap after that one. All right, so in this case here, our iodide is going from -1 to 0, which means it is being oxidized or reduced. It is being oxidized, right? So on our number line there, it is going from -1 to 0, becoming more positive. It is actually the Mn here that is starting at +7, which would be here, and ending at +4, which would be in this direction, becoming more negative, which means it is being reduced. So that is being oxidized, that is being reduced, and our oxygen is not doing much, right? So it's not doing much there. So at this point, what we want to do is really just break this off into 2 half reactions. One obviously would represent the oxidation half reaction, and one would be our reduction half reaction. The simplest way is just the elements that look alike on opposite sides. So those two look like eyes, so I'm going to put those together. And this guy has an Mn. And so does this guy. So I'm going to put those guys together as well. At this point, the next thing that we want to do, since we actually already identified, again, this is our oxidation and our reduction. This also means that our reducing agent, right, would be this guy. And our oxidizing agent would be this guy. Once we have it like that, we want to balance all the elements other than hydrogen and oxygen, which means in this case, we need to put a 2 in front of our I minus. And in the case on the bottom there, we have 1 Mn and 1 Mn, so we don't have to worry about that. That's all good to go. Once we've done that, we are now going to move to oxygen. The first half reaction has no oxygen, so we don't need to worry about it. The second half reaction on the left-hand side has 4 oxygens. On the right-hand side has 2. Which side needs the water? The right-hand side, and we need 2 waters there, right? That will give us 2 more oxygens. Once again, because we added 2 waters there, we do need to go to the left-hand side and add 4 H pluses to balance out the hydrogens, so we're not short any hydrogens at that point. Any questions up to there? At this point, we are ready then to balance the overall charge on each side by adding electrons. So again, we want to add it to whichever side needs the negative charge. And if we look at our first half reaction, overall charge here is -2. Overall charge here is 0, which means it is the right-hand side here that needs a couple of electrons. That will then give me a -2 on the right to match the -2 on the left. I can feel pretty confident about that because this is my oxidation half reaction. And I just put my electrons on the right-hand side, which is where they should go. So that, again, that's why it's kind of important to maybe figure out what's the oxidation reduction so you don't screw up when you add your electrons. So by some chance, if you put electrons on the left at this point, you should know that should be wrong because it should always be on the right because that's the oxidation one. Looking at the bottom one here, this guy is contributing a +4, which is 4 times +1. I'm going to look just at the overall charge here on my polyatomic ion, which means this is contributing a -1. That means overall charge here on the left-hand side is +3. Right-hand side, this guy is contributing 0, and this guy is contributing 0, which means the overall charge there on the right-hand side is 0 at this point. The side that needs the negative electrons is the left-hand side, and we need 3 electrons to contribute -3, which now takes us to 0 on the left to match the 0 on the right. Any questions so far? All right, at this point, we are really at the step to add them back together, but we are in a little predicament here. We don't have the same number of electrons in each, so we do need to fix it. In this case, we actually need to fix it by multiplying not just one half reaction, but we need to multiply both half reactions by a number. The common number between 3 and 2 is 6, right? So we would need to take our top half reaction there, and we're going to multiply it by 3 to get us to 6 electrons. We will do a similar thing to the bottom one, except that we need to multiply by 2 to get us to the correct number of electrons. So I'm just going to kind of kill some of this here. So I can rewrite it. So rewriting both of those reactions underneath here and multiplying them across. For the top one, I end up with 6I minus, gives me 3I2 plus 6 electrons. Multiplying the 2 for the bottom guy there gives us 6 electrons plus 8 H pluses plus 2 of the MnO4 minus and 2 of the MnO2 and 4 waters. At this point, we can now add these guys together because we have the same number of electrons in each half reaction. And those electrons, once again, should always completely cancel out. The idea here is however many electrons somebody loses should be the exact same number of electrons that somebody gains. So once again, should always cancel out. I think in this case, once again, that is everything that will cancel out. So everybody's on the left-hand side of the arrow and both equations stay there. So that will give us 8H pluses plus 2MnO4 minus plus 6I minus. Right-hand side, 3I2 plus 2MnO2 and 4 waters. This technically should be the balanced equation in acidic conditions because it says H plus. Just to make sure really quickly here, we got 8 hydrogens on the left, 4 times 2 is 8 on the right, 2 Mns on the left, 2 on the right. We have 2 times 4 here for 8 oxygens there. 4 oxygens there plus 4 more over there gives us 8. And 6 I's on the left and 3 times 2 on the right is 6. Overall charge on the left there is plus 8 from this guy, minus 2 for this guy, and minus 6 for that guy. That is a 0. Overall charge over here, nobody's contributing anything, so that is 0 over there. And that means that it is, again, is balanced correctly in acidic conditions. Any questions up to that point? Obviously, if you were doing acidic conditions, you put a box around it and move on with your life, yes. But again, here we are doing basic conditions, so we do need to do one more step here to turn it into basic conditions. So remember to turn your sort of acidic guy into the basic. This is the point where we will add OH minus to both sides. And once again, the OH minus that we are adding will be equal to the amount of H plus that there is. So in this particular case, there's 8 H pluses, which means to the left-hand side, we will add 8 OH minuses. And to the right-hand side, we will add 8 OH minuses. Once again, the side that has both the H plus and OH minus will combine to make water. And that will give us 8 waters, which in this case, we have 4 on the right, which means that this guy will reduce down to 4 waters on the left. And that should do it here. So let's see, we end up with 4 waters plus 2 MnO4 minus plus 6I minus goes to 3I2 plus 2 MnO2 plus 8 OH minus. And once again, we should still be balanced. So 4 times 2 is 8 hydrogens on the left, 8 over here on the right. We got 4 oxygens in the first one, 8 more oxygens in the second. So that's 12 oxygens, 4 oxygens here and 8 here, which is 12. 2 Mns on both sides, 6 iodides on both sides. Once again, overall charge on the left there is 2 times minus 1, which is minus 2, and 6 times minus 1, which is minus 6. That's a minus 8 to match the minus 8 that we have over here. And we are balanced in both cases. We know that this, again, is a basic solution, or done to be basic, because we see in the final result here, OH minus, which symbolizes that it is basic. Any questions on any of those steps? So it takes some practice, yes. But again, if you follow those steps, don't mess up rewriting something, you'll be in sort of good shape, hopefully, I would hope. Any questions on how to follow these steps here? Okay, then what I think we'll do now is we're going to look at a couple of problems there from the study assignment. That is study assignment with letter F. And just to make sure everybody's on the same page in terms of what you need to do. So let me, I think I have one on here that matches, I hope. That's fun stuff. All right, I believe this is from your study assignment, like the very first question, maybe? Is that the very first one? Okay. So you have on the very first sort of question, like basically guys that look like this. And there's a number of things that you want to do and should do in this case. You need to make sure you do it so you get the points. First off, it wants you to go through each of the elements here and give the oxidation states, I think, above it. So if we were to do it for this particular one here, going through our Cl minus, you would give the oxidation state a -1. For the oxygen, it would be -2. That would give you a -6, which means in this case, the chlorine on the right is going to be a +5. So that is one thing that you need to do on that little table there. You need to make sure that you identify the oxidation states for each of the elements. Remember that you got to include the charges. You then need to decide what you are looking at. Is it the oxidation half reaction or is it the reduction half reaction? So on this very first question, you just have half of the problem, basically. You have either the oxidation half reaction or the reduction. In this case, we would be looking at the chlorine. It's the same element on each side. Chlorine goes from -1 to +5, oxidation or reduction. It is oxidation. Once again, if you follow that, it is starting at -1, ending at +5, becoming more positive. So you need to identify that this is a oxidation half reaction as part of what you need to do on that question. So I believe it is make sure you give the oxidation states. I believe it is make sure that you identify it as either the oxidation or reduction half reaction. The last thing you're going to do is actually balance this. And you're going to balance it in acidic conditions, I believe is what it says. Yes. So that is basically what we just did, but you're just going to do it for just this half of the reaction. So you would start just like we were doing those problems a second ago. And the first thing that we would want to do, right, is balance all the elements other than oxygen and hydrogen. In this case, the chlorine, there's one on each side, so we're good. The next thing we should do, right, is balance the oxygen. So which side would need the water in this case? Left-hand side would need 3 waters, which means the right-hand side would need 6 H pluses. Yeah. And the last thing we do before we add them together is add the electrons. So that's what we would want to do here. Left-hand side, this guy is contributing 0. This guy is contributing -1. This guy is contributing -1. And this guy is contributing 6 times +1 is +6. That means the right-hand side has a +5. Left-hand side has a -1. Which side should get the electrons here? The right-hand side, how many electrons? It is 6 electrons. Because if I take 6 electrons, that now is a -1 on the right and a -1 on the left. It is not 5 electrons like I always want to put, but it is 6 electrons to take you back to -1. And we know that is good because we've already identified this as a oxidation half reaction, and we just put the electrons on the correct side for that. And that is what should go on the line there, I think. Yeah, is this? So you want to make sure that you do all of those things for each of those questions there. And I think those were all the 3 things. Read the instructions to make sure, but identify the oxidation numbers for each of them. Again, they should have positives or negatives depending on the charge. Is the overall half reaction you're looking at the oxidation or reduction half reaction? And again, you need to balance it with the waters and all that kind of stuff. Any questions? I don't think it asked about oxidation agent, reducing agent, and oxidizing agent, did it? In the instructions? No? Okay, then I think you're good on that. All right, any questions on what to do on that question there? Okay, then let's talk about the next set of questions, basically. There's a bunch of them coming up next. So I think this one, is that the first one you got up? Yeah, okay. So let's take a look at this. So these are the equations that you're going to be given. And personally, they kind of have extra stuff in there. And the purpose of the extra stuff is, well, probably really to make it easier to grade for the instructor. But It's probably truthfully their answer there. But it also tells you what type of equation you should do here. Should you balance it in acidic or basic conditions? And in this particular case, I see this H plus, which tells me I should balance this in acidic conditions. So personally, what you should do is look at the H plus and know that you should balance it in acidic conditions. You also should take the water, and frankly, you should remove them for now. So you're going to take these guys out, but this does tell you that you do want to balance this in acidic conditions. And what you would do is, like we were just talking about, start with the equation that looks like this, so you don't get confused. And at this point, what we would do is, again, just follow our normal steps. We would take our MnO4 minus, and it would be matched up with the other Mn. We would take our sulfur guy here and match it up with our other sulfur guy. And once again, here we would add our water. Actually, we would balance everything other than oxygen, which in this case we don't have to worry about because we have one Mn on both sides and we have one sulfur on both sides. So then we would move to oxygen. Top guy on the right would need 4 waters, right? And because of the 4 waters there, we would also need the 8 H pluses over here. For the guy on the bottom, the water should be added to the one on the left, as there's 3 oxygens on the left and 4 on the right. So we would add our 1 water here and our 2 H pluses to this side. At this point, we're ready to add our electrons. Overall charge on the left-hand side is going to be +7, and that is a 8 from this guy and a -1 from that guy. Overall charge over here is a +2. Which side needs the electrons in this case? It is the left-hand side, and we need like 5, I think, in this case, right? By the way, I didn't do it before, but this should tell me this one is being oxidized or reduced. It is being reduced. Electrons are on the left-hand side, yeah. And we know that because if we did it, this is a +7. And that is a +2, right? Which means it is going left and becoming more negative. This, by the way, is a 6. That's a +4 action there. That is a -2, -8. That's a +6. So the sulfur is going from +4 to +6, becoming more positive. It is being oxidized. If we look over here, overall charge is -2 coming from this guy. Over here, we have -2, and this guy is giving us +2, which means 0. This side that needs the electrons in this case is the right-hand side, which also makes sense because this is our oxidation one, and we would need 2 electrons in that case. Yeah. Any questions up to that point there? All right. We're ready to add these together, but once again, we cannot add them together because we do not have the correct number of electrons in each. And once again, here we're going to need to multiply both half reactions. Common number between 5 and 2 is 10 by multiplying them together, right? That means the top reaction here needs to be multiplied by 2. Bottom reaction here needs to be multiplied by 5. And once again, I'm just going to write it underneath. So top one multiplying the 2 to everybody gives us 10 electrons plus 16 H pluses plus 2 of the MnO4 minus gives me 2 of the Mn2 plus and 8 waters. Multiplying the 5 to the bottom equation gives me 5 waters plus 5 SO3 2 minuses, 5 SO4 2 minus, and 10 H pluses. Get the calculator here, and 10 electrons there. Now that I do have the same number of electrons, we can add these guys together, do a little reducing action here. So definitely, as we've talked about, our electrons are on opposite sides. They should completely cancel. In this case, we have a couple other things that will sort of reduce. Right-hand side, we have 10 H pluses, right? Left-hand side, we have 16. That means all 10 of these will get rid of 10 of those and leave us a net of 6. We also have waters on opposite sides, right? On the left-hand side, we have 5 waters. Right-hand side, we have 8 waters, which means all 5 of those will get rid of 5 of those and leave us with 3 waters left over. And I think that's all the canceling we got going on. So at this point, we're going to keep everybody on the left and keep everybody on the right. So that will give us 6 H pluses plus 2 of the MnO4 minus plus 5 of the SO3 2 minus goes to 2 of the Mn2 plus 3 waters and 5 of the SO4 2 minus. And once again, this should be the balanced equation in acidic conditions. I have 6 hydrogens on the left, 6 on the right, 2 Mns on the left, 2 on the right. I have 2 times 4, which is 8 oxygens, and another 15 over there, which is a lot of oxygens, 23, I think. Over here, I have 3 oxygens there and 20 here, which is 23. 5 sulfurs, 5 sulfurs. Overall charge on the left is plus 6 and minus 2 is plus 4 and minus 10 is like minus 6, I think, if I did that math right, or maybe not. So that is minus 10 and plus 4 is minus 6. I did the math right. That's good. So we are balanced on each side. So the reason why the H plus and H2O are in there is really for you to like make it easier. But you could check yourself. My H plus ended up on which side when I was all done? The left-hand side, which is the same side it started on. And my water ended up over here, which is the same side over here. So you could check yourself at the end. Make sure you actually got everybody on the correct side. But I would take it out. They put it in, I think, for grading purposes, because they wanted you to come back through and put coefficients and just make it easier to grade. But take those out. If you see H plus, it means balance it in acidic conditions, and you would follow those steps there. Any questions on that? Now, if we look at one more here, just to show you the basic version, which would be this. So this is E, I think, maybe. So once again, you will see that there is OH minus and water. So if you were to balance this guy, I would once again recognize that basically that means you should balance it in basic conditions. But to start with, get rid of those and just start with it like we were doing with just this equation, and then go off and do your balancing magic. Yep. At that point, but obviously balance it in basic conditions. Once again, when you have it correctly balanced at the end, you will find the OH minus on the right-hand side, it should be, and you'll find the water over there on the left-hand side where it should be. But again, don't leave them in there as you try to balance it, because you'll probably mess yourself up. So take them out and just use that to know if you should do acidic or basic conditions. If you don't see anything there like H plus or OH minus, it's like probably neutral conditions, just like balance some electrons and add them together, and you'll be in good shape, kind of like a basic one. Any questions on how to do any of these things here? All right, well, this is fun stuff. So on Thursday, we're doing our actual experiment. So it is a physical experiment. So make sure you got shoes, goggles, all that good stuff. It is the one that's on the desk here. It is this stuff right here. So it's like redox stuff. So I'm going to say these 2 ones from this week will be due at the end of the week, both of these. Yeah, so give you some time to work through it and all that good stuff. Any questions on anything? Okay. Have a good night if you're out. If you want to continue to work on it, you're